Good morning. Today we will be studying the application of second law to a chemical reaction. Last two classes we have studied in details the application of first law or the conservation of energy to a chemical reaction. Now we see application of second law, application of second law, application of second law in a chemical reaction, in a chemical reaction. Now, what the second law tells about a chemical reaction? To know that, you will have to know one thing, that there are two types of reaction. One is irreversible reaction, another is reversible reaction. One is irreversible reaction, another is reversible reaction. But you see, in the field of engineering science, there are many words which are repetitive. You will see that in fluid mechanics, shock is used in compressible flow, again shock is used in turbo machines. There are like many words which are repetitive, but they do not bring the same sense. This reversible, irreversible is not in our thermodynamics reversibility, irreversibility. This reversible and irreversible reaction means, if we consider a reaction like this, gamma A, that was all right. You give me that one, hello. Gamma A, keep it, this is okay. Gamma A plus gamma B equals to gamma C. For example, I give this direction, gamma C plus gamma D. Let this is. It is not always necessary to give this stoichiometric coefficient. You can write, when you do not balance it, C plus D. Now, when this reaction proceeds in only one direction, that means only A and B produces C and D. C and D, that is the products, cannot be converted back to the reactants. That means opposite direction reaction is not possible. Then this is known as irreversible reaction. That means if you start with A plus B as reactants, we get C plus D as products, and these products are not reverted back to the reactants. That is known as irreversible reaction. The reaction goes in one direction. Under certain circumstances, for certain reactions, the reaction takes place in both the directions. That means A plus B is converted to C plus D and CD are converted to AB. That means both these reactants give these products, the products are again converted back to the reactants. This reaction is known as reversible reaction. The one directional reaction is known as irreversible reaction, and this reaction, which is not in one direction, which can take place in two directions, both the directions. That means the products can be converted back to the reactants known as irreversible reactions. Now, there are two things. First of all, you have to find out, you have to know what is meant by equilibrium. Equilibrium of a chemical reaction. Equilibrium of a chemical reaction. Equilibrium of a chemical reaction. What does it mean? When in a chemical reaction, the species in the medium, the concentration of the species, temperature, pressure, everything remain invariant with time. That is then this is known as equilibrium of a chemical reaction. How the equilibrium takes place? In case of a one directional or irreversible reaction, C plus D, if it is a one directional or irreversible reaction, then the equilibrium will be achieved when one of these reactants or both the reactants is totally consumed to produce C plus D. If the reactions take place in stoichiometric coefficient, then both of the reactants will be consumed simultaneously. Otherwise, one of the reactants will be consumed fast. For example, if you give excess air, then the fuel, if this is fuel and this is air, if you give excess air, then the fuel will be consumed fast. That means either one of the reactants or both the reactants are consumed completely, then the reaction stops. In that case, whatever is the constituents, their composition, pressure, temperature, they are fixed. That means this is the equilibrium condition. Clear? For example, if we consider CH4 plus 2O2 is CO2 plus 2H2. That means when both the reactants are consumed to produce this, then this composition will be fixed, pressure, temperature will be fixed, and then this will correspond to an equilibrium condition. But what happens when the reactions takes place in both the directions. That means A and B converted to CD and CD will be converted to AB. Then how the reaction equilibrium will take place? Before that, one has to know in this type of reaction, the net reaction when the reaction process continues, where the A, B, C, D, all the species constituent, all the constituting species vary in their concentration, means the reaction should proceed in a one direction. The bulk reaction should proceed in only one direction. That means if it proceeds in left direction, means the rate of reaction from left to right is more than the rate of reaction from right to left. That means there is a net depletion of A and B and there is a net production of C and D. So reaction can proceed in left direction, reaction can proceed in right direction, the net reaction. And this happens when the reaction proceeds in the left direction, this happens when A plus B producing C plus D, this rate is more than the rate of reaction which takes place from C plus D to A plus B. When these both the rates balance, that means neither reaction proceeds from left to right nor from right to left, then the mixture contains A, B, C, D are all fixed amount, concentrations are fixed. So therefore this corresponds to the equilibrium of chemical reaction. You understand? So second law of thermodynamics deals with these two aspects, that for a reversible reaction, in which direction the reaction will take place, the net reaction will take place in which direction, number one. And number two, if this attains an equilibrium, either equilibrium or left or right net, there are three options. Which options will be there? Now if the option is the equilibrium, that means the forward rate and reverse rate are same, then what will be the equilibrium compositions of A, B, C, D? This is furnished by the second law of thermodynamics to the chemical reaction. Now let us consider a chemical reaction like this, nu A plus nu B, a complete chemical reactions, but it is a reversible chemical reaction. That means the products can be converted back to the reactants, and reaction, that means the reaction can take place in both the directions. And let us consider this reaction take place at a constant temperature and pressure. We know that in this type of reaction at constant pressure and temperature, for the equilibrium to achieve, probably you know these things, dG at constant temperature and pressure will be 0. That means for a physical process, this is the second law which will be applied. Probably you know these things, earlier we discussed the Gibbs function. There are various ways we impose the directional constraints as given by the second law. One of the ways, as you know, the entropy change of the universe in a process has to be greater than is equal to 0. In a cyclic process, we know the cyclic integral of dq by t is less than equals to 0. In all the cases, equality signs represents the equilibrium conditions and inequality sign represents the feasibility condition. Similarly, the Gibbs function at constant temperature and pressure should always be less than 0 for a process to be feasible. That means for a physical process to occur in a particular directions, the Gibbs function at constant temperature and pressure should be less than 0. And at equilibrium, it should be equals to 0. So combining these two, we can write dGTAP less than equal to 0. Okay. If we write this, then we can write another step. This of course you have to accept at this moment. This is not so far taught to you that dGTP, that is the change in the Gibbs function at any temperature and pressure for a multi-component system having A, B, C, D, E, F, r number of components, dGTP is given by sigma mu I dni I1 to R, where mu I represents the chemical potential of ith component, chemical potential of ith component. Rather, I think it will be better if you start from here. The chemical potential of ith component in a multi-component system is represented or defined like this: del G del N I. That means with respect to the, that is the partial differential of the Gibbs function with respect to the number of moles at constant temperature, pressure and other moles. That means J naught is equal to I. All other moles are kept fixed, only the mole of that particular component is varied, and then this partial differential is defined as the chemical potential. Mu I is the chemical potential of the ith component. This comes from here. We consider G is a function of Tp and mass, but in case of multi-component system, it is N1, N2 dot dot Nr, the number of moles of all the components. And if we make a total differential of it and use the definition G is equal to H minus Ts, then you get this expression mu I as del G del Ni. Actually this is defined like that. If you get this, you will get dG is equal to V dP minus S dt plus sigma, if you write this equation, del G del Ni at Tp, you write this thing and Nj, J not equals to I. That means if you del G, then you can write del G del P dP, del G del S dt, sorry here Tp, del G del P dP, del G del T dt, and if you use this equation you get this thing. That means this thing is nothing but del G del T at del G del P at constant T and N, okay, dNi. Very good, very good, very good. And this thing is nothing but from the definition it will come, del G del T at constant P and N. So if you make use of this and the definition of this GH minus TS and this, you can define this, and this quantity is defined as the chemical potential of the ith component. Only this much information you have to know. I am not going into much detail because so far you have not been taught this chemical thermodynamics or thermodynamics of multi-component system. So if you do so, for this reaction I can write dG T and P equal to what? If I use this equation mu A dNA plus mu B dNB plus mu C dNC plus mu D dND. Clear? Now this change in the number of moles in a reactive multi-component systems are not independent. There is another constraining equation. What is that with respect to this equation? dNA by gamma A is equal to, if we give a minus sign for one case, that means the reactants, then we have to give a plus sign because these are the changes, differentials. We have to follow the sign. dNc by gamma C is equal to dNd by gamma D. That means another constraining equations for this change of moles are given by this. They are proportional to their stoichiometric coefficient, the change in the number of moles. If you use this here, alright, if you use minus dNb, if you use this here, then what results you get? If you use this here, you will get dGTP at constant temperature and pressure is equal to, if you write this way, mu A gamma A plus mu B gamma B minus mu C gamma C minus mu C gamma D times dNA, any of this gamma A, that means any of the reactants has to be there. You see that this was this thing, I just replaced dNA, dNb, dNc, dNt by any of this proportionality. That means any of these terms which are proportional to each other. I express everything in terms of dNA by gamma A, so that one dNA by gamma A will come. So these quantities will be positive and this one, and this will be less than equals to 0 for the feasible process. Clear? Now there are two conditions. One condition, if mu A gamma A plus mu B gamma B is greater than mu C gamma C. What does it mean? Mu C plus mu. That means the product, sum of the product of the chemical potentials and the stoichiometric coefficients of the reactants is greater than the sum of the products of the chemical potential and the stoichiometric coefficients of the products, then the reaction should proceed from reactant to products, A to, that means from left to right, left to right, to right. That means what is left to right? A plus B, C plus D, because in that case dNA has to be less than 0 to make this less than 0. It is clear? But if other way, that means mu A gamma A plus mu B gamma B is less than mu C gamma C plus mu D gamma D, that means this quantity is positive. That means, sorry, this quantity is already negative. That means dNA gamma A has to be greater than 0. That means Na has to be produced. That means from right to left. So right left nomenclature is used. That means A plus, that is net reaction will take place from C plus D to A plus B. It is clear? That means it depends upon the relative magnitudes of these two sums. When mu A gamma A plus mu B plus gamma B is greater than this will proceed from. That means when sum of this is actually the chemical affinity. That means if this is more here than this, it will go in this direction, DNA is negative. When this is more than this, that means mu C gamma C plus mu D gamma D. That means sum of the products of the chemical potential times the stoichiometric coefficients of this side is more than this side, the reaction will proceed from this to this. In that case, dNA by gamma A has to be greater than 0, because the final constraining thermodynamic equation is dGTP is less than 0. At equilibrium, mu A gamma A plus mu B gamma B is equal to mu C gamma C plus mu D gamma D at equilibrium. This is known as, this is at equilibrium.
This is true for all the reactions.
This is true for all reversible reactions, and this equation is known as equation of reaction equilibrium. This is true for equation all reversible reaction, equation of reaction equilibrium. When in irreversible reactions the products can never be converted back, we don't apply this thing. The question may come, why don't you write this equation and see for an irreversible reaction? And if we go on seeing that, you will see for an irreversible reaction, this is true in this case, that this is always greater than this one. So this cannot come back to this. So this is true in that case what Professor Das has asked, that this is true for all situations. And we specially apply this for reversible reactions. Mainly the question of equilibrium comes when both that means it is a very nice thing. In unidirectional reaction, equilibrium condition will come when actually the chemical reaction is stopped. One of the reactants will be consumed. Which one will be consumed first? That reaction will stop. Sometimes two may be consumed simultaneously if we use the stoichiometric coefficient. There will be no reaction, equilibrium. But in a reversible reaction, you see the equilibrium condition is there. It is chemical equilibrium. Truly it is not equilibrium. Processes are taking place. That means reaction in this direction and reaction in the opposite direction, that's same. It is almost the same at a steady mass in a control volume. Mass is invariant with time, control volume is steady with the mass, but the mass flux processes are not ceased. Masses are coming out and going out, coming in and going out, and they balance each other. This is the same concept for the reversible reactions. All right. Now we will find out an expression for this equation of reaction equilibrium. Our final objective is to find out the composition, equilibrium composition. Now we know that there is an opportunity, or there is an instant when the reversible reactions are in equilibrium, both the directions, the rates are same, chemical potentials are same. So therefore equilibrium takes place, and this equilibrium composition. What is equilibrium composition? What is equilibrium composition? Okay. This equilibrium composition, to find out, we have to make an expression, we have to develop an expression for this reaction equilibrium. First I write the reaction equilibrium again. Mu C gamma C, I write in this fashion. Mu D gamma D minus mu A gamma A minus mu B gamma B is 0. That is true. That is the reaction equilibrium equation. That means the equation will be, the constituents will be under equilibrium, and this equation has to be valid. Now if we consider ideal gases, all reacting constituents as ideal gases. Now I consider ideal gases. This is one assumption. So whatever I will deduce now, it is valid only for gas reactions. All right. Now if we write the ideal gases, now we can write that mu of an ideal gas, ith component, which is ideal gas. I am not repeating ideal gas again and again. This can be written as at any temperature and pressure, rather it is a function of temperature and pressure, can be written as its value at this temperature and pressure. Pressure means this is the pressure of the ith component, the partial pressure. Its value will be like this, plus RT ln xi. This thing you will have to accept at this moment. This will not be deduced. If the multi-component thermodynamics of multi-component system could have been studied, I could have taught you in detail, then the deduction will be there. That means the chemical potential of an ith component in a mixture of multi-component systems at temperature T, any component will be at the same temperature of the mixture, but at the partial pressure, depending upon the constituent compositions and the number of components, can be written as this chemical potential at T and the total pressure of the mixture plus RT ln xi. What is xi? Is the mole fraction. Now this can be written as, so this chemical potential of any component at the same pressure, that means the total pressure of the mixture and the temperature, can be written as the molar Gibbs function of the ith component. So this part you have to, this is R bar, universal constant. When I deal with mole fraction, this will be universal. So therefore mu I, this particular expression is very, very important. Now mu I, that is the chemical potential of the ith component, is equal to his molar Gibbs function, is equal to his molar Gibbs function at that same temperature and pressure of the mixture. What is this molar Gibbs function? That means when this component will exist as a pure component, you understand, as a pure component, the same temperature and pressure, this is as a pure component. What is this molar Gibbs function? Plus R bar T ln xi. So if you accept this equation, then if you put this here, what you get, you tell me what you get, G, then you get gamma C. Now I write this is GC, G bar C, G bar C plus gamma D, G bar D, and this is at same temperature and pressure, this Gi at that same temperature and pressure of the mixture, GID, rather I write this way, that will be more explicit, gamma C, G bar C at temperature and pressure plus gamma D, G molar Gibbs function for component D at the same temperature and pressure of the mixture, minus gamma A, G bar A at the temperature and pressure. Any question you can ask me. If I do any mistake, you also detect it. GB, T and P. I substitute this. Then the remaining part is R bar T ln, which is interesting in a sense that xc to the power gamma C, xd to the power gamma D, xa to the power gamma A, xb to the power gamma B. Clear? This is clear? So I write this expression. So this part for all these 4 is equal to 0, I am sorry. This part makes this. Now this is nothing but the change in the Gibbs function due to chemical reaction at T and P, because it is the Gibbs function of the product minus Gibbs function of the reactants. For a reaction, gamma A plus gamma B, if you take this reaction, gamma C plus gamma D. So this part, if we just express, can you see this? This part, if we just express this part as delta GR at T and P, then we can write plus R bar T ln, again I repeat it, xc to the power gamma C, xd to the power gamma D, xa to the power gamma A, xb to the power gamma B is equal to 0. So delta G at Tp is this plus this minus this minus this. Clear? Now what I do, I just update G at T and P to G at T and some reference pressure P0. How to do it? This is simple, this you can understand. If you recollect your earlier definition, dG, molar Gibbs function, is VdP minus SdT. Molar Gibbs function for a pure component, when the ith component is the pure component here. It is for all pure component. This is all right. At constant temperature I update pressure VdP, and for an ideal gas this dG is equal to, what is VdP? V is RT by P, RT dP by P, which I can write ln dP by P, d of ln P, I am sorry, d of ln P. dP by P I am writing d of differential of ln P. This is the technique of writing these things, RT d of ln P, ln P by P0, sorry there will be, I am sorry, dG is RT ln P by P, dd ln P, all right. Now therefore G minus G0, that means rather I write this way, G of T and P minus G of T and P0, that means you integrate this RT ln P by P0. I require this expression. That means GTP is GTP0 plus this, rather I should write this one more explicitly, GTP0 plus RT ln P by P0. Now everything I will not write, you just now follow. If I substitute G at Tp for all this C, D, AB in terms of G at Tp0, that means then this part will be resembling this with Tp0, Tp0. That means delta G at Tp will be delta G at Tp0. Alright, that means we can write delta G at Tp0. But an extra term will come when I will express this. RT ln P by P0 will come out into gamma C, RT ln P by P0 into gamma D, RT ln P by P0 minus gamma A minus gamma B, so that ultimately this will be added with R bar T, RT means R bar T, I am sorry, R bar T ln XC to the power gamma C, XD to the power gamma D, I think you can follow, XA to the power gamma A, XB to the power gamma B into what? P by P0 to the power gamma C plus gamma D minus gamma A minus gamma B. Clear? Again I am telling that I am expressing this, this is at delta G at Tp. Now I express this, that means this will be gamma GC bar, that is molar Tp0, Tp0, Tp0 T, that means which is defined as delta G at Tp0, which is the Gibbs function of energy, Gibbs function of, sorry, Gibbs function of not energy, reaction at standard state, at standard pressure, at standard pressure. Clear? So therefore standard pressure or reference pressure P0. So this will be an extra term will come R bar T ln P by P0, which will be multiplied by this stoichiometric coefficient, positive and negative, which is raised as power in the ln, because this ln was already there, they are clubbed together. Okay, that means the little algebraic thing will do that. Then we can write this thing, if you recollect this, then we can write this thing Xc to the power gamma C, Xd to the power in a different fashion. That means what I am writing, because the space is small, so I cannot, and this expression is equal to 0, I am sorry, always is equal to 0, because I am writing this expression and I am substituting this one in here. So therefore is equal to 0. So I write this equation now in this form. Please check in your note, gamma A, XB gamma B into P by P0 to the power gamma C plus gamma D minus gamma A minus gamma B. This thing is equal to exponential, that means I am writing in other form, minus delta GR, because this will go to other side of the equation, divided by RT. This is the final equation. Now this part you see is a function of temperature, this part is a function of temperature, let KT, because R bar T, sorry, R bar T. So delta GR at Tp0, this is a standard pressure, reference pressure, it is a function of temperature. Temperature is fixed, then the Gibbs function of equation, reaction is fixed. So Gibbs function of reaction, like enthalpy of reaction, internal energy of reaction, is, that means it is the change in the Gibbs function of the products minus reactants at that temperature. These are all function of temperature. So this part is a function of temperature, and this part which is a function of temperature is known as equilibrium constant. Equilibrium constant. Equilibrium constant. That means this is a function of temperature. That means for a reaction at equilibrium, if the temperature is known, I know the equilibrium constant. If equilibrium constant is known from any tabulated values, then I know that this equilibrium constant equals to this. That means this give a constraining equation if I know the pressure of the equation. If it is an atmospheric pressure or standard pressure, usually this is atmospheric pressure, then this part is 1, otherwise this will give a numerical value. That means we get a constraining equations for the mole fractions of the equilibrium mixtures. I get constraining equations from the chemical equations, and these two things are solved together to find out the values of Xc, Xd, Xa, Xb. Clear? So this is the theory, and this theory will be made more clear if we follow this example now. Okay? Very simple example. Gaseous methane, quickly, gaseous methane CH4 is burned to its 60% of theoretical amount of air. So far we have discussed earlier with 200%, 400% theoretical air, 60% theoretical air, okay, in a steady flow process at a pressure of 10 kilonewton per meter square. Both the fuel and the air are supplied at 25 degrees Celsius. The products which consist of CO2, CO, H2O, H2 and N2 in equilibrium leave the combustion chamber at 1000 K. Okay? That means they leave the combustion chamber at 1000 K. Determine the composition of the products and the amount of heat transfer in the process per mole of methane. That means per mole of methane we want to know if this be the products of combustion, what will be, this is the equilibrium. They are in equilibrium means that they do not change in their composition. CO2, CO, H2O, H2, N2, they do not change in their composition. So what we have to find out, and the composition of the products, that means when the products are coming out, they are of fixed compositions. We have to find out that composition and the amount of heat transfer in the process per mole of methane. The equilibrium constant K for the reaction is given. That means this is the reaction which is taking place. That means what happens when carbon dioxide and hydrogen, they are reacting with each other and they are producing carbon monoxide and water vapor. That means since this is not a complete reaction, what happens, this reaction takes place, CO2 plus H2 gives CO plus H2O. That means always this reaction is taking place in the backward, forward and backward direction at 1000 K, and the equilibrium constant is given as 0.693 for this reaction. This will be clear if I just proceed with this example. Now enthalpy values are given like this. Temperature, these are the different temperatures. 25 degrees Celsius is the temperature at which the methane and air was supplied. 1000 K is the combustion products temperature, and these are the constituents CO2, CO, H2O, CH4, N2, H2. Now you see how we proceed this equation. First of all, we have to write the equations, chemical balance of this equation. Now how can I write CH4 plus what? 0.6, what is the stoichiometric? 2O2 plus 2 into 3.76. Now the question comes, sir, why CO is coming? That is the concept, because the complete formation of carbon monoxide and hydrocarbon breaks, but it cannot completely form carbon dioxide. If this was 100% theoretical air, 200% no CO business, CO2 plus H2, CO business is still there, you will see afterward, because for a complete reaction it is not the amount that required, it is the time you have to give. And in a steady flow process definitely it comes with the residence time, that means you will have to give the residence time, that means the space, the time for mixing and the time for the flow, that means the time is important. However, I am not complicating this thing by telling that, but if we consider time is sufficient, then obviously theoretical air or more than that will give you the carbon dioxide. So therefore here carbon dioxide is there and carbon monoxide is there. But let us start with a mole of, these are unknown, carbon dioxide per 1 mole of methane. Then you see I am not going into all details, I am writing in one step The carbon monoxide will be 1 minus, that means I am trying to reduce the number of variables. If I write A moles of carbon, carbon is there only 1. So therefore 1 minus ACO will be there. I will make the balance of O from the left hand and right hand side. You understand my strategy? This is an intelligent way of doing. Now let I know B H2O. If B is the H2O, then probably you can follow 2 minus B is H2, because always I balance the H2.
So excuse me. So in this case, will the entire methane be burned, or there will be some?
Entire methane is burned means what? That is a, just a minute, I will explain everything. 2 into 3.76. Nitrogen is very funny. Nitrogen, what does it do? That it, as it is the left hand right hand side. The entire CH4 is burning means what? CH4 is not there, but it is converted to CO2 and CO. If all the CH4 is converted to CO2 and H2O, then I could have told this complete combustion is there. Now when there is a CO and H2, from the enthalpy point of view, this can again burn with oxygen and give water vapor and carbon dioxide, which could liberate more enthalpy. Very loose term, more heat will be generated, though it is not a correct term from thermodynamics point of view. That means more temperature will be increased. That means there are some burning elements remain. That is the reason for which this type of burning reaction or combustion reaction is called incomplete. That means still we can exploit enthalpy from this. So therefore this is the concept. That means CO2 and H2O could have been there fully if there was this thing or more than this. When 0.6 with the deficient oxidizer, this CO and H2 come into picture. But concept lies somewhere else, I am telling. Now first of all, balance this at a school level concept, you quick. Balance the O2, I am writing the equation, balance O2. Balance O2. I get A plus B is 1.4. Nothing else is required to be balanced, because I have written the equation like that. So balancing of the mass, that is mass balance, gives a relationship between the moles A and B. A plus B is 1.4. It is clear? Completely clear? Now the concept is that this is the product. Then one can question, sir, finish. I know that this is the product, but why are you making a complication that the product is equilibrium? That means this is because there is a reaction which is possible. That reaction is this reaction, CO plus H2. Okay, this is the reaction, CO2 plus H2. That means this CO2 and H2 under these circumstances, you see that under these circumstances, that means these products CO2 plus H2 can react to give CO plus H2O. And again CO plus H2O, this is chemistry. We don't have to put our head much in it. That means only we can understand that among these constituents in the products, they are reactive. And this reaction is possible. CO2 and H2 are reactive with each other to produce CO and H2O. Similarly, CO and H2O have the affinity to react with each other to produce this. When one claims that I get a product with fixed composition, means that these reactions are in equilibrium. That's why at the beginning of the problem it is told that the equation defined by this, the reaction constant or what equilibrium constant Kt at that temperature of 1000 degrees Celsius, where it is coming out, is 1000 degrees Celsius, sorry, 1000 K is 0.693. Initially it is difficult for you people to appreciate why these reactions come into consideration. This is because in the product this reaction is possible. If this reaction could have taken place in a net in one of the directions, then one of the constituents CO2, H2, CO, H2O could go on changing, or 4 of the constituents go on changing, not one. So if it is going in this direction, these are depleted, these are produced, increased, vice versa. But this is in equilibrium. This concept is clear. Now I use this value 0.693 is equal to X CO2, X, I am sorry, X CO, X H2O, X CO2, X H2 into 1. Why? Just now I derived the equation. Where is this? Just now I derived the equation. This is this, XC, gamma C, XD, these are the products, XAB, P by P0 is 1 here, 1 atmospheric pressure, okay, 1. 0.01 kilonewton per meter square, that is P0. So therefore x of CO to the power 1, it is 1 1 1 1. So this is KT. So we have to find out now XCO, XH2O, XCO2, XH2. Clear? What is this? XCO is, first of all, you now here forget this. What is the total number of moles? A plus 1 minus A plus B plus 2 minus B plus, what is this one? This one is 4.512, 4.512, and ultimately this becomes 7.512 because this B cancels, A cancels, 2 plus 1 3, 7.512. Clear? So therefore X CO2 is how much? X CO first. CO is how much? What is CO? 1 minus A by 7.5. Actually 7.512 will cancel. So we can write, because this is all to the power 1, only the moles we can write. So a clever boy will write this 1 minus A into B divided by A into 2 minus B, because denominators of all these are same, total number of moles. Be careful, don't do that. If 1 is square, then you are gone. That means by stoichiometric, this is to the power 1, this is to the power 2, this 1, so 1 left. So be careful, when the indexes are same, that means the number of moles cancels from the numerator and denominator, so it is the mole. So this is equal to 0.693. Well, so you can find out one equation, this, another equation, so 2 equations, so you can find out values of A and B. Equilibrium composition is fixed. That means you can write the equation and you can tell what is the, now the mole fractions. Now you require 7.512. For CO it is 1 minus A by 7.512. For, now I write X CO2, now A and B, yes, I give the value. A is equal to 0.526 and B is equal to 0.873. Therefore, the answer is that X CO2 is A by 7.512 with these values of A. What is X? X CO2 is, I do not know whether my calculations are correct or not. X CO is 1 minus A by 7.512, which comes 0.063. Now X H2O is equal to 0.874 divided by 7.512 is 0.116. I have written 0.874. Why? It is 0.873. So it is 0.873. So it will be 0.8. I have written B. However, X H2. What is H2? H2 is 2 minus B. 2 minus 0.873. These are all primary school level calculations. 0.15, and Xn2 is 4.512, that is the number of moles of nitrogen, left hand side, right hand side same, divided by 7.512. So you can give it. And now you can write the chemical equation. Chemical equation, if it is not asked, then also you have to write, if you have to find out the heat transfer, the next part, which is the application of first law. The first part is the application of second law. Now you write the equation. Equation writing will be very simple now. Now this will be CH4 plus 1.202, that's 60% of this, plus corresponding N2. You see your class note initially is equal to, now A is known, 0.526 CO2 plus 0.474 CO plus 0.873 H2O plus 1.127 H2 plus 4.512 N2. Complete. That means the reaction, this is the chemical equation. Next part is very simple. What is Q? Q is simply you find out sigma HP minus sigma HR. Sigma HP is what? CH4. Now you require this, where is that? Table. Simply you find the values. Oh God. Now I write Q is equal to sigma HP minus sigma HR. Now you see your note that sigma HP is 0.526 CO2. CO2 is at which temperature? 1000 K. You don't have to go to internal enthalpy of reaction and all these things. Straightforward the enthalpies are given. You just put that. What is the enthalpy of CO2 at 1000 K? Minus 360 into 10 to the power 3 in terms of kilojoule. Plus, now I am evaluating this. Next is 0.474 number of moles. The entire analysis is based on 1 mole of methane, CH4, fuel, 0.474. What is CO? Minus 88. Very careful, be very careful about putting the data and temperature. Products are at this temperature. So therefore, don't take the data from this column. Then after CO, what is that? H2O. Okay, H2O is how much? H2O का क्या है? 0.873. 0.873, oh, 10 to the power 3, 0.873 into minus 214 into 10 to the power 3 plus, it's a lengthy one, plus what is there? CO H2O, H2 number of moles 1.127, H2, where is H2? H2 21. These are all products. Now I am seeing the chemical equation and doing it, 21 into 10 to the power 3 plus 4.512 into N2, N2 का क्या है? 21 into 10 to the power 3. So this is sigma HP minus sigma HR. What are HR? CH4. CH4 at what temperature? 25 degrees Celsius. It is not 0. That is its enthalpy of formation. That is its enthalpy of formation, molar enthalpy. It has to be there. What is this value? So this something there is wrong. Minus 75. Yes. Minus. So this is 0 for N2H2. I am confused. CH4 is minus 75. What? 1 mole. This is on the basis of 1 mole. The equation CH4 is 1 into minus 75 into. Very good. Minus.
Sir, not minus 2, sir, just 3.
That's all. Why? O2 and N2, 1.2 O2, 4.51 20, it will not come. 0. Very good. 10 to the power 3. 0. All right. So this gives you the key. Please. This is the concept. Huh?
3 moles of S2.
Huh?
Now then these two will react, so moles of CO2 will reduce and moles of S2 will
Just a
also
minute, just a minute. Let me find out what you want to tell. I don't know. Yes, this one. Please tell. CH4 reacts with O2 gives, we have assumed that A1 minus AB, yes.
Yes, sir. So when CO2 and S2 will react, so moles of
CO2 and H2 will react, yes.
So moles of CO2 will reduce.
That is not reduced. That reaction, that is an equilibrium. What I have told so far, you have not listened to it. You ask your friends, he will explain this to you. This reaction is an equilibrium, both the directions. So far, the entire theme of the today's study is this. That means this will react forward and reverse direction reaction the same. They are in equilibrium. That's why there is a reactive, there are reactive species which can make reaction in both the directions. And they are in equilibrium, and that is the reason for which you get fixed compositions of the constituent products. Okay? This I told many times. If this reaction could have taken place in any of the directions, net directions, which I started at the beginning of this lecture, then it could have been depleted, it could have been produced, or this could have been depleted, this could have been produced. That depends upon this condition, that mu A, gamma A, all these things I have, mu B, gamma B. So this equality, greater than or less than mu C, gamma C plus mu C, gamma D. So if it is greater than this, it is this direction, less than this, it is in this direction, and equals reaction equilibrium, from which we derive the expression for the equilibrium constant. So this reaction is at equilibrium, then only we get a constant composition mixture. Clear? All on a sudden, please don't ask question. That is stupidity. Try to show your intelligence all on a sudden, waking up from a nice sleep in the class and then ask the question. This at least I told 4 times that this is the case where you get a constant composition. Otherwise you could not get it. Either CO2 was continuously depleted, H2 depleted, and these are produced. And until and unless it is totally consumed, this reaction totally stopped, is continuously taken, but it does not happen so. When it takes place, that is just like your other transport processes, then the sum of this, that is the chemical affinity, sum of the products of the chemical potential times the stoichiometric coefficient of one pair is going to be reduced, another pair is going to be increased, so that at some condition they are balanced. And this is the subject of chemical kinetics, and it can be proved from chemical kinetics also that the reaction equilibrium will occur when the rate of reaction in the forward direction equals to the rate of reaction in the backward direction. We conceive it in this way that both the reactions balances each other, but exactly the opposite in such a way that the reaction ceases to occur. And from the chemical rate equation, that chemical kinetics, one can express the same results which we have done from the consideration of thermodynamics, that the expression for the reaction equilibrium. That's why you will see in chemical kinetics books also the expression for reaction equilibrium is there. Though there is a distinct difference from chemical kinetics with thermodynamics, as I have told in the very first class of thermodynamics, that thermodynamics deals, classical thermodynamics deals with equilibrium system. They do not deal with the rate of transfer of energy, which is dealt for heat in heat transfer, which is dealt for momentum in the momentum transfer or fluid mechanics. Similarly, for chemical equations also, this rate of equations is dealt with the subject chemical kinetics, which is as distinct from thermodynamics. But the concept of chemical equilibrium is still there, and the same equation can be derived from the consideration of chemical kinetics. But we have derived it from the consideration of thermodynamics. Please ask any question. So therefore, second law tells under what condition the chemical equilibrium will exist for a reversible reactions. Whether or not chemical equilibrium will be there or not, if chemical equilibrium does not exist, in which direction the reversible reaction will occur. Alright. So these two things are very important and to be predicted by the second law of thermodynamics applied to a chemical reaction. And first law is the typical conservation of energy, where you have to understand the enthalpy of formation. How do you define the enthalpy of formation or internal energy of formation? All elements, okay, having zero internal energy and zero enthalpy at the standard conditions, 25 degrees Celsius and 1 atmospheric pressure, 100 kilonewton per meter square, say approximately 101 kilonewton per meter square. Whereas the compounds do not reveal that. Compounds reveal some enthalpy, which is the enthalpy of the reaction by which the compounds has been formed from their elements at that condition, standard conditions. Clear? Okay. Thank you.